Okay, what's up guys? New video for your ass. Now, you might have noticed that the colours and lights look a bit different in here. I got a new light strip and it is like the freaking sunshine in here. I can't see, well I can see excellently actually, but it's all a bit strange because it's different to what I'm used to. It's just so bright everywhere. The scope, I had to readjust the settings, but actually it looks better now. But I've got this kind of janky scope like sun visor hood, because if I take this away, you see what happens to the scope. It just kind of like gets this light on it, so just got to keep that over there. Anyway, I've repaired a lot of these amplifiers, but I just thought, I don't think I've ever really done a kind of feature, either repair or going through the circuit and telling you all about these amplifiers before. So obviously with the kind of onslaught of Fullbridge amplifiers coming out of Brazil and them gaining popularity, Korea Zenon factory, actually specifically Zenon, these ones have, you know, they designed their own Fullbridge amplifier board to compete with the stuff coming out of Brazil, and obviously to keep in people generally all like, yeah, Korean is the way to go, don't touch that Brazilian stuff. Like, so Zenon factory thought it would be a good idea to jump on board with the Fullbridge stuff. Now, what I will just mention is Fullbridge is ancient technology, as is half-bridge technology. You can look back as far as like the JL Audio 500/1 or the JBL GTO 14001 or a bunch of the Alpine MRD, like Alpine did a whole bunch of Fullbridge, which is basically a Brazilian board, but nobody knew it because it's Alpine, so it's fine. But yeah, Fullbridge is as old as ass, and but people think that it's new because all these small Brazilian amplifiers coming out. And the only reason that they are small and new and efficient is because they're using modern MOSFET technology, modern drivers, low RDS FETs, so they don't generate much heat, so they don't need a lot of FETs because they're high current, they don't generate a lot of heat, so they don't need a big heat sink. Everyone thinks there's something brand new and crazy. So but anyway, I wanted to show you what's going on with these boards coming from Zenon factory in Korea and how they've gone about creating a Fullbridge design pretty quickly without actually having to spend too much money on R&D. So here we have, the board looks pretty small. This is what's called the M14K, or something 7000. This is basically a 7K. So this is a 7000 watt RMS amplifier, and as you can see, it's pretty small. These actually pretty heavy, but yeah, very compact, very compact. It's a very kind of baby style old school design. As you can see, you've got a whole bunch of smaller transformers on here, which is more like what you'd see in the old half-bridge designs. But yeah, this is in fact a Fullbridge. So what Zenon have done is they've been like, oh, we need to create a Fullbridge amplifier here. We want to make something Fullbridge. We want to make something smaller. We want to make it full range. We want to make it higher efficiency. We want to make it cheaper. So rather than spend a whole load of money on employing some really like experienced and high-class amplifier design technicians who are, you know, well suited in this stuff, they took a look at their catalog. They took a look at their schematics for their half-bridge boards, and they were like, well, these half-bridges amplifiers are strappable. That's technically Fullbridge, just outside of the heatsink. So what if we take the same amplifier, the same drive circuit, basically basically a Korean half-bridge, and we just squash them, use fewer numbers of new MOSFETs instead of larger numbers of older MOSFETs, use the same drive circuit, but put them together in the same PCB and bridge them. This essentially is what we have here. So I'm going to use my phone camera for this because it's better than these jank webcams from like 2001 that I'm using for the streaming. So let's start with the power supply section here. So the power supply drive architecture, as you like, is the same stuff as all the half bridges. And to be honest, this stuff doesn't really need to be changed. The power supply is just a power supply. It's just converting 12 volts into a higher voltage plus minus rails for the output section to use. So there's been no developments in that's not affected by being half bridge or full bridge or whatever. So the power supply is essentially the same. The Brazilians do it slightly differently, but this power supply section is the same as all the stuff they used to from the old Korean half-bridge amplifiers. It is just a TL494 chip, which is then buffered by a bunch of NPN and PNP drive transistors here, which is then given to the power supply MOSFETs. So the main difference between this style power supply and the Brazilians is that the Brazilians tend to go for just one large transformer, whereas on this one from Korea we have multiple smaller transformers. I'm sure there are some benefits to and for and against having one large versus 6 smaller. I'm not too well versed on the characteristics and physics of transformers. In my head I imagine that 6 smaller ones might be beneficial because the peak saturation for each smaller one might be higher when you combine a bunch of small ones compared to one larger one for the same voltage and the same current output continuous. But yeah, I think that's okay. You know, I'm quite happy to see that. Another thing that I quite like is that because we have such small stuff going on here with like such small transformers, each transformer only uses one push and one pull MOSFET per transformer. So we haven't got a bunch of MOSFETs running in parallel on the same transformer. And that helps to negate paralleling issues with using MOSFETs in parallel, being whether their VT is slightly different or their RDS is slightly different. So by having minimum amount of MOSFETs running in parallel is ideal. So that's actually something that I probably prefer maybe over the Brazilians. Yeah, so that's okay. The power supply MOSFETs that are being used here are absolute beast and they cost a fortune. This is IRFP 7530. These are very high current, very low RDS MOSFETs, and yeah, they can provide a bunch of current and not get very hot at all. So power supply is very good. I'm actually happy with this. I'm more happy with these power supplies than I am with a bunch of the Brazilian ones which use the PIC to generate the PWM for the... Yeah, I don't like that. That sucks. Use the TL494. It's reliable, it's stable, it's designed for generating waves like this rather than the PWM with its own integrated oscillator. Anyway, yeah, so power supply is fine. So with the output section, this is the bit what I really want to talk about in how they've designed a Fullbridge amplifier without spending a whole bunch of money. So with an old Korean half-bridge amplifier, if you've been watching my videos for any decent amount of time, you will have seen me do a whole bunch of these type of repairs. The typical Korean half-bridge amplifier consists of an output section which is split up into 4. So you have quad parallel amplifiers inside the same PCB that are all paralleled after the inductors. So you'll see 4 output inductors, sometimes 2, but most of the time 4 output inductors. And the MOSFETs that are being used are usually FDA24N40F or FDA24N50 and a whole load of them. And each quarter of this amplifier, each one of the 4, is driven by an IRS21844S drive IC, which are kind of fragile and they run quite warm. But they've been okay for many years and they've been in like literally thousands of different brands of amplifiers and stuff. That's the general Korean style output section, and China do it as well. That's what you'll generally be running if you're running a half-bridge amplifier from any of those China or Korea places. So with the Brazilian amplifiers, they're not using that kind of drive architecture anymore. What you've got is depending on the brand, Banda and Triumphs do it slightly differently. For example, you'll have the PWM generated by a bunch of IC chips rather than discrete components like op amps like you have with these ones. These use like a combination of a couple of 072Cs and there's an LM211 in there. Basically it's basically the way that the amplifier takes the sine wave and converts it into pulses to drive the Class D architecture is quite old school, and it's done with individual components on these, whereas with the Brazilians, that circuit which does that is integrated into a chip, and then in order to split it off into the 2 sides of the bridge, there is a chip that also does that. It's like a logic converter type thing, and the drivers that the Brazilians use are often IRS2010S, which are again not particularly new, but they're pretty solid. I quite like those. JBL use those, and actually loads of brands use those for the output drivers. And the Triumphs are using silicon instrument drivers, I can't remember the exact number. Silicon instrument drivers. They seem a bit fragile. But anyway, back to this one. What this is pretty much the exact same circuit as the half-bridge amplifiers that Korea have been banging out for years, but it's just a full-bridge version of that. So on this driver card, we've got a pair of IRS21844S drive ICs, and then this one, the 7K, we've got 2 obviously amplifiers, one half of the bridge and the second half of the bridge, and then the output MOSFETs in this are IRFP 4768, which again are pretty badass output MOSFETs, not too bad. However, using this old drive circuit for this full bridge design, and they've sped up the switching frequency to make it full range, this is not the best way to do it. This is not the most effective way to do it either, and that is shown by the way that this output section works, these MOSFETs, these output FETs, are not driven very well at all, and they really do run quite warm. They run hot. They don't parallel very nice at all. So you have two low side and two high side, for example, on this one. On the bigger version of the amplifier, the 10K or 21K as Vibe call it, I'm pretty sure you got 4 FETs paralleled, I think it is. And these massively low RDS, high current output FETs, they don't like being paralleled. Any slight tolerance difference between the FETs, even if they're in the same batch, will cause heating. So something about this circuit, whether it's the old style drive circuit, whether it's these drivers, these buffer drivers, which are actually in between, they're buffering the RS21844S, or the fact the switching frequency is too high for these FETs, or the inductor parameters aren't right, something about this circuit hasn't been designed very well. And compared to some of the Brazilian brands that I have worked with, these are hella unreliable. I've repaired countless of these, all with the same kinds of issues, randomly killing 1 or 2 FETs in the output section. These filter capacitors, after the inductors, they explode. And just by probing around and looking at the shape of the low side drive wave and stuff, you can tell that this hasn't really been optimized. This circuit has been rushed and thrown together to get it out to market, to say, hey, we now offer a Fullbridge option for you that is cheaper, more efficient, blah 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 blah. This isn't a circuit that has been completely stripped back to the drawing board and built up and, you know, designed or with modern drive circuit and, you know, with this whole kind of Fullbridge thing in mind. It's just parts picked and taken from older amplifier designs, made into something that works as Fullbridge and sent out to market. Now, despite that, if you can get these for a good price, they're not a bad deal. Okay, this is a decent amount of power and it's pretty efficient in a small package, and the components that he's using, like the FETs, the capacitors, everything's assembled well, and the components are high quality as well. Apart from perhaps the drive circuit, I wouldn't have used that drive circuit, but although the reliability may be hit and miss, it seems to be that you either get a good one or you get one that's not happy. There's been cases where guys have ran these for years, even like wired down as well, and they've been absolutely fine and they don't run hot, but you've had other guys that have gone through a few of them and haven't done anything wrong, and the amp's died on like low volume or idle or something. So it does seem a bit hit and miss, but I'm not saying that they're absolutely terrible amplifiers. I'm just saying that the way that Zenon has approached this in designing a Fullbridge amplifier, they've not designed it from the ground up. This is just kind of a Fullbridge version of their old half-bridge stuff, and as a result it does have its issues. In terms of repair, the most common thing, like I said, that comes in one of these amplifiers is the output MOSFETs will randomly die. They've not been pushed hard in any of these cases. Most of these that I have come in, they've died on low volume or idle, or, you know, the guy's using it as a daily, not even competing it, or it's wired. I've even had a couple that have been wired to 2 ohms, not even 1 ohm, up to 2 ohms, and the output FETs have randomly died. And it's never all of them, it's usually just like the odd one here and there. So I'll have ones that come in with just like 1 high side, 1 low side, or even just 1 single FET will go down. And when you see on the thermal imager in a bit, I might even have a picture somewhere I can show you, the uneven heating of these on idle. So when you turn the amplifier on, just on the bench like this, out of the heatsink, and you have no signal, no load connected, it's just idling, right? In most amplifiers, the output MOSFETs, A, don't get warm at all. B, if they do get warm, they heat up evenly and only very slightly. However, on these ones, you'll have one FET randomly getting to like 50 degrees Celsius, the other one sitting at 22, this one over here is at 34. So you can tell that there is an imbalance here. You can tell that one of the FETs is fighting the other. Small tolerance differences are not taken into account for, and they do run uneven. So I'm betting that the ones that come in that have like single dead FETs or like random stuff like that, it's where there's been one FET that the tolerance was just a little bit too much out on, and it has just overheated and died over time, not even being run hard. Even just sitting idle, that would have happened. So that is the most common cause of failure. The other cause of failure, like I said, is these capacitors here in the output section. These things are filtering, I think, after the inductor. So basically what happens is any spikes that the inductor hasn't filtered out, the inductors aren't perfect at filtering high frequency, and the spikes do get through and stuff like that. So these capacitors will be responsible for filtering out any of those, especially when you're clipping. When you're clipping, these capacitors work freaking hard. So these, I don't believe, are high enough voltage from the factory, and if the customer is clipping quite a lot, or you know, even if the inductor hasn't quite been wound as good as maybe some of the other ones, that's another thing. Obviously, these are physical things, and each one it has a different geometry. The way it's wound, it won't be exactly the same as the last one. So yeah, I don't believe that these are high enough voltage to deal with the spikes coming off the inductors, and I've seen so many where these capacitors are just completely exploded. I repair them. I fit much higher voltage versions of these capacitors with the same capacitance, and I haven't had any back yet that I fitted new ones to. So yeah, output FETs and these capacitors are the main things that I see. I mentioned how the power supply was pretty solid. However, there is one thing that this massively falls down on, and it doesn't help when you have the issues in the output section like this. These TL494 style power supplies, and the way that the protection circuit works, it's not very fast. The Brazilian protection circuits are actually remarkably fast. The fact that they are PRC controlled as well, that really helps. So the way that the protection circuits are designed on the Brazilians is really good. Usually if you kill some MOSFETs in the output section, the amplifier will just be in protection mode. Even if you try and power it up multiple times, because those amplifiers go through a health check first, you are very, very unlikely to kill the power supply section as a result of output section failure, unless a protection circuit fails to kick in for whatever reason, but most of the time it kicks in fine. However, on these Korean style amplifiers, they are using this old tried and tested power supply design. The protection circuit usually doesn't kick in time, and it also disables the protection circuit while the amplifier is powering up. These don't have a health check mode whatsoever, so each time you power the amplifier up, the power supply is needing to fill these rail caps with high voltage, and obviously capacitors, when they're empty, are pretty much like a short circuit. When the capacitor's empty, it will just be presenting a near short circuit, which then increases in resistance as they charge up. So this amplifier needs to be able to dump a huge amount of current in an instant into the capacitors when it powers up. So if protection circuit was limiting current, like it would protect every time you turn it on. So basically the protection circuit isn't active for the initial turn on period. Now, what happens if you've got a dead MOSFET in the output section, literally presenting a short circuit across any of these rails? Well, the power supply, when you switch the amplifier on, will try and send voltage and current into that short. And obviously, being a short will massively stress the power supply section. Usually what happens is it saturates these transformers, and when you saturate a transformer like this, it then presents a direct short to the power supply FETs, which then all explode. So what you end up with is, going from one shorted MOSFET, you end up with a shorted MOSFET, all the power supply FETs dead, loads of power supply gate resistors dead, and the power supply gate buffer transistors also dead, simply because the protection circuit didn't kick in time, and it doesn't have a health check mode at the start when you first power it up. And that is exactly what happened to this one. This one has come in and it has two dead MOSFETs in the output section, one here and one here, from opposite sides of the bridge, from separate sides of the amplifier. So this is essentially channel 1, this is essentially channel 2. Now the reason for that, it could be that one of these MOSFETs failed, and obviously things are happening super lightning fast in electronics and switching and stuff like that. So when one of these MOSFETs fails, it will basically turn off, it will deactivate one side of the bridge, and then for a brief moment, for a few fractions of a second, this side of the amplifier will have been driving the speaker independently alone, and it also then will have not been really grounding properly, or it will have been grounding to DC. So this might have even sent DC. Yeah, it probably would have done. So then when this FET blew, these won't have been producing audio anymore. It would have just been this side, which would have put a strain probably on this side of the amplifier, and maybe blown one of these FETs as well. It's difficult to tell exactly why an amplifier has failed when it's just got dead output FETs. It can be a whole number of things. But anyway, either way, like I say, two dead output FETs, and the others here remain fine. They don't show any signs of getting super crazy hot or anything like that. So just two random dead FETs. And as a result of that, we also have a completely smoked up power supply section. This whole bank of FETs was like blown to pieces, loads of soot on the board and stuff. Dead gate resistors over this side. Also the gate buffer transistors, which are in the middle of the board here. So these are actually what are driving the power supply MOSFET gate. These are badly damaged as well, and that is proven by the shape of the wave on the scope when I try and probe the gate. It's really bad shape. So that's the most common repair I get for these. They're not a difficult repair, just mainly because I'm so experienced with the old half bridges. I can apply all that information onto these boards. They're pretty much the same, just the full bridge configuration. But I just thought I'd give you a little lowdown on what Zenon factory is offering in terms of Fullbridge at the moment. These amplifiers, like I say, they come in brands varying from Vibe or here in the UK and Edge in the UK. Overseas, I think DS18 have an amplifier that's the same board as this, and probably some other brands as well are using these boards. So if you're good at looking at amp guts and recognizing amp guts, then this board, this is Zenon Fullbridge, and now you know all about it. So that's enough of me talking. Let's just crack on with the repair and get this thing up and running again. If you don't care about seeing the repair, you can obviously shut off the video now, but if you want to see this get back up and running and what I have to do, actually I think it's probably just going to be changing FETs at this point and drivers, but stick around. So I've actually already taken all the old FETs out from the power supply, as we can see here, and I've also changed 1, 2, 3 gate resistors that were completely burnt out. There are 3 here that remain, and these 3 that remain are in the push or the pull. These are in the 180 degree bank, and these were fine. These didn't short to PNP, so these are fine. No reason to change these whatsoever. Still reading 22 ohms. They haven't been stressed, but I've changed all of the ones in the 0 degree bank here. But what I do need to do is I do need to change all of these drive transistors in the middle of the board here. See these? So we've got 4 per side, and we have 2 PNP and 2 NPN. The NPN transistor, which in this case is the one marked with a C, this one is actually what's responsible for passing the drive wave onto the MOSFET gate. It's the one that beefs it up, gives it a bit more current behind it, and to drive these very difficult to drive high current MOSFETs. The PNP is actually just responsible for turning the gate drive off. So when the MOSFET needs to be turned off, obviously the signal goes down to ground, but it needs to be pulled off very quickly so that it doesn't remain on when the next one turns on. If they're both on at the same time, that will cause them to heat up. So they've got to be turned off really quickly, so that's the job of the PNP transistor here. I'll just show you on the scope screen why I need to change these. So if I probe the gate pad here, this is what the drive wave should look like. This is on a good bank. So we have a drive wave here that rides up to about 10 volts, just under 10 volts, and then turns off very sharply. Very sharp up, very sharp down, and it averages off to about 6.1 volts RMS. That's what it should look like. If I switch over to the other side that got more badly damaged and we probe the gate drive, you can see here this is what I've got over here. I've got a 1.4 volt RMS wave that's very rounded and doesn't look too nice at all. Very slopey on the down, very swingy on the up. If I probe the 180 bank of that side, that looks good, but the other side, that almost looks good. 5.1 volt RMS, but this doesn't turn off quick enough. It's got a bit of a little up on turn off, and it's not the correct voltage. It's about a volt down. So this is another reason why you really must be using an oscilloscope to repair amplifiers. If you know what to look for and you have repaired amps with a scope before, it is possible to get some amplifiers up and running with just a multimeter and no oscilloscope. However, it really is important to check the shapes of these waves, because sometimes using a multimeter, just by checking the VRMS of the drive waves, gives you a good idea as to whether they're okay or not, but you can't check the shape of them. Sometimes the shape is really important. I've had amplifiers where you would never find the fault with them that was actually occurring with a multimeter alone, and a scope would have been required. So yeah, a lot of questions always ask me, can you do amplifier repair without an oscilloscope? No, not really. Get one. It really is an insight into what the amplifier is doing. Cool, so they're all out. Now the parts I like to use to replace those with are, for the NPN, I just use a BD139, which is a pretty decent enough transistor to use. It's beefier than the original. Yeah, it'll just provide a nice strong drive for the MOSFET. But the more important one is the pull down, and for that I like to use a 2SB772. You also have the KSB or KTB 772. These are much more beefy than the originals and much faster at being able to turn off that drive when the signal turns off. So yeah, I just, where I can, like to use better parts. So yeah, 2SB or KTB, KSB 772 and BD 139s for the NPNs. Okay, let's check the drive waves now those new parts are installed. That's better. Very nice indeed. 6.1 volt RMS, sharp turn off on that bank, sharp turn off on that bank. It looks identical. We're looking for these waves to look absolutely identical on the 0 degrees and the 180 degrees bank. Yeah, that's proper banging, that is. So that's ready for new MOSFETs now, so let's go ahead and whack these beefy 7530s in the board. Alright, cool, that's all 12 new power supply FETs fitted. So now what we can do is I'm going to power it up and check, first of all, that we have the rail voltages in the correct places on the output section. Make sure the drive circuits aren't buggered completely. And then when the rail voltages reach a certain height, the output section will try and start switching. So we're going to see whether the output section still works or not, or whether it has drive circuit issues. The FETs which still remain in the output section appear to be okay. They don't appear to be damaged or shorted just by multimeter tests. However, they can still be internally bad and still be internally weakened by whatever caused this amplifier to go down in the first place. So even if they work in the circuit for this idle test and it all switches and looks okay, they're not to be trusted to keep it. It is tempting to keep them in the amplifier and, you know, just fit some small banks with the rest of the places that were missing now and reuse these FETs, but it's not a good idea, and they won't necessarily last because they may have been damaged by whatever caused this to fail. So we can use them just to power the amplifier up a few times to make sure the drive circuit works, but then remove and swap and replace them with a fresh new batch of output FETs, which again is pretty expensive. These are pretty beef-ass ones, 4768s, and then it'll be good to go provided the drive circuit is okay. The drive circuit isn't quite the same as FETs. Like, if the drive circuit works, it's fine. It's not. There's not really going to be a case where the drive IC gets a little bit weakened and is now going to die sooner than it would have otherwise done. They're so fragile anyway that anything that would cause any damage in them would prevent this from working. So you don't have to change the drive circuit if it still works. So for the first power up test of the output section, I'm only going to allow a lowest voltage into the amplifier, 10.5 volts, and that is directly proportional to the rail voltages. So by applying a low input voltage, we get lower voltage rails, which is just safer for everything. So what I'm going to do first is just pulse the remote for a brief fraction of a second, which will build a few volts on the output rails, and that's enough for me to see whether the drive circuits are shorted or not. So let's just pulse the remote, get a tiny little bit of voltage in the rails, as you saw there. That was the power supply drain, doing a little square wave. So now if I go over to the output section, I should have positive rail voltage on the drain of the high side, which we do have them. So I'm going to pulse a little bit more, get a little bit more voltage. 8 volts there on the high voltage rail. That should be present on both these FETs. And on the low side, we should have negative rail on pins 1 and 3, which we do, and nothing on pin 2. So this side, the drive circuit appears to be not completely shot to bits, because if it was, we'd have voltage in the wrong place. On the other side, we have negative rail voltage there on pin 1, nothing on pin 2, and on the high side, nothing, high, nothing. Cool, that's looking pretty promising so far. So now I've confirmed that the drive circuit isn't completely shorted. I can power it up fully, allow a little bit more current to pass. I was only allowing 2 amps, so let's let, like, I don't know, 5.5 amps in. And what I'm going to do is hold my oscilloscope probe on the low side drain, which will give me a square wave, a switching square wave, rail to rail switching when this thing starts to operate. So let's hold that there and look on the scope screen for a large switch wave. Fingers crossed it comes. Ta-da! So only drawing 3.2 amps at idle, which is pretty nice. The relay has clicked in. We have a nice wave there, 84 volts RMS on the low side drain, and over this side we have 84 volts again. So that's looking pretty good. So obviously the drive circuit survived. If they didn't, they wouldn't be doing that. I'm just going to go over to the power supply section, turn the power supply off, and just feel for heat on the back of these power supply FETs. Just make sure that none of them are getting, you know, super hot, which they're not. So there's no uneven switching going on there on the power supply, no gate resistors or diodes that have gone. That seems absolutely fine. They're stone cold still. So cool. Now all I need to do is to take the output FETs and fit them, and this will be ready to go. However, with an amplifier like this, because I mentioned how fussy these MOSFETs are running in parallel and how badly this drive circuit has been designed, it's not wise to just fit the FETs randomly in the amplifier like this. You can do that with most amplifiers that aren't so fussy and with FETs that aren't so fussy, but with these ones, it's really good practice to take each FET and measure its parameters on a transistor tester like this and group them into groups of same VT and same RDS. VT is the more important one. VT and CGS. VT meaning turn on voltage, so the voltage on the gate which causes the FET to turn on. That needs to be exactly the same for FETs in parallel, otherwise they will turn on at different times and heat each other up. And the CG is the gate capacitance, and that needs to be the same as well, because if it's wildly different then you'll have ringing from one FET and not so much on the other FET, which can cause issues driving in parallel as well. So even though these FETs are from the same batch tolerance is a thing, and so I just want to make absolutely sure that we are putting as closely matched FETs as possible in parallel with each other. And so that being the case on this amplifier, we have parallel FETs, 2 low side here and 2 high side. So I want 2 matched FETs here and 2 matched FETs here. Ideally, we want to closely match the low and high side if we can, but it's not as important as them being directly in parallel. And over the other side again, 2 here and 2 here. We want them to be as closely matched as possible with each pair. So I'm just measuring the MOSFETs now, and they seem to have a VT of 4.3 volts, and they're all pretty much the same, and a gate capacitance of 14 nanofarads, which is pretty good. The fact that these are all really identical, that's really good for this amplifier, because it doesn't like it when there's tolerance differences. So I'm just making different piles. See, this one's a 4.2. Now, 0.1 of a volt difference on a VT is not the end of the world. It's not going to cause mad issues. We've got slightly lower gate capacitance, but that could just be test variance. So even though this is not an issue, I'm going to just put this in a separate pile of 4.2 volt ones. And, you know, I'd like to try and match them up as perfectly as I can. So we're going to put all the 4.3s together in batches in parallel with each other, and the 4.2s. This is another 4.3, so I'll put that in that pile. Our new FETs are fitted. Obviously, every time you fit the FETs, just check gate resistors. I'm checking between the 2 parallel ones. So we've got 12 ohm gate resistors, so we should have 24 ohms between each parallel gate, which we do. Check that on that side, check that on that side. They're all fine. So let's power up. Okay, so keep an eye on the scope for the low side switching wave, rail to rail. And let's go. Let's turn her on and see what happens. There we go, 3.3 amps drawn at 10.5 volts. Relay is engaged. Now I'm just using my thermal imager to have a little peek and see if any of these FETs are getting warm. Now that it's turned on and it seems happy, I'm just going to increase the voltage slightly. I'm going to go up to 12 volts. And as you can see, that has increased the current as well. Okay, so in terms of output FETs, in terms of heating, yeah, this has got nothing to do with the VT. Ha! What the hell? These amps are just a big pile of doo-doo, hey? So, after that small amount of time having the amplifier turned on, we have this FET here, which is one of the ones that I did. This is one of the ones that was like a slightly different VT. This one here is getting very hot, whereas this one here is staying very cold. Like, so we've got hot, cold, hot, hot, and then over this side we've got hot, cold, hot, cold. So, but yeah, this is normal with these boards. If you're repairing one of these, this is normal. It does this with these FETs. The only way I've got it to not heat the FETs like this is to install different MOSFETs that are easier to drive, like the I think this is the smaller one. I think I put 69N29s in. It might have been I put 69N25s in the even smaller one. They do a 4K version. Put 69N25s in that one. That sorted out heating differences with these. they do just run hot on the output FETs, and that is just a characteristic of this circuit. And like I say, I don't believe that it has been designed particularly well. Let's just show you guys, for you guys who are into amp repair and stuff. So you might be thinking, okay, so if it's getting hot, then that should be because they're not being driven correctly. Let's have a look at the low side drive wave. That can often tell us a lot about the health of the drive and whatever. So I'm going to go ahead and probe the low side gate, and we're going to see what the drive wave looks like on there. And for that, I'm going to turn my scope to AC coupling, which will prevent it being way zoomed out on the negative rail. Ta-da! Okay, so this is the low side drive wave. As you can see, it's a bit on the curvy side on this way up. And this bump here, this is due to the insane amount of gate capacitance that these FETs have. This has like 14 nanofarads of gate capacitance, which is humongous. And as a result, you get this great big boof when the FET turns off, and the residual current from the gate is then dumped back into the sort of gate drive line from the FET. And then when it's switched on as well, you get this kind of boof, because it's very hard to drive. So that's the low side gate drive of one of these FETs. Let's check the other one. That's looking pretty much the same. If we go over to the other side, these ones are running a little hotter. Again, it looks the same. And the same here. I'm going to pause my scope on here from this side. I'm going to go over to the other side and unpause it, and that will show up any differences between these. They look identical. Do you see that? There's like a slight difference in the curvature, but no, the drive waves are identical between all of these. However, they are all heating differently. And actually, just out of interest, let's check the high side drive wave. Not that you can really tell a lot by looking at the high side drive wave, just because it's so big. It's like rail to rail, so it's difficult to really get an idea. But let's have a look anyway. So yeah, this is the high side drive wave. You know, nothing there really that is any cause of concern. So. And like I said before, I have fitted different FETs to these that are slightly easier to drive, and they do not all heat up. It's actually very, very happy with slightly easier to drive FETs in. So this is not an issue with the amplifier, you know, being broken and still having an issue that needs repairing. This is just a design, poorly designed amplifier, the way that it heats these FETs up like this. Even though I matched them perfectly, like especially on this side, all the FETs were matched perfectly for VT. These ones are still heating unevenly. So yeah, keep that in mind if you're ever repairing one of these. Don't worry too much. Most amplifiers, I would say, worry if you have output MOSFETs getting hot, but in these ones the switching frequency is high. Actually, it seems to be amplifiers that have a very high switching frequency, full range ones like this, tend to actually have this problem more often than the lower switching frequency ones. So like if you're repairing a full range, like a 4-channel, like from B2 Audio or Crescendo or one of these, which is a Class D full range 4-channel, then those output MOSFETs do run hot on idle as well. So I think it is just a characteristic of having the high switching frequency. Let's just have a quick look actually. What is the switching frequency? I think it's we've got 130. See, that's not actually that fast. That's not even really that high. That's about the same as the bass amps. That's about the same as the half bridge. See, like on the actual proper full range Class Ds, like the 2 channels and 4 channels, that switching frequency can be up as high as 350 kilohertz. On this 125, that's not too far off what it is on the old half bridges. So yeah, it's not frequency. It's not as a result of high frequency. Then apologise. It's not particularly high frequency, the switching here. I think it's literally just that these FETs don't like being run in parallel, and this drive circuit was not designed with that in mind. Cool. Well, as far as I'm concerned, this is a successful repair. We'll need to reassemble this into the heatsink, of course, and run an endurance test for about 45 minutes on various static loads and also reactive loads, just to make sure it's, you know, reliable after the repair. It's not got any issues that are just waiting to happen. So we'll do that, and then it will go off back to the customer. What some of you with a keen eye may have noticed is that the original MOSFETs for this amplifier were soldered to these little heat pads. These are electrically insulative, but they have a good thermal transfer. They're soldered to the MOSFET, and then that clamps to the heatsink. However, in order to remove all of these from all of the power supply FETs and the output FETs and resolder new ones, it's just a little too time consuming, and obviously time is money. So for my hours worked on this, that equates to my labor charge. So it actually works out cheaper for the customer for me to actually just not install those and use SILPAD 900, the thermal pad, like the orangey stuff, that has just as good a thermal transfer, and these, like I say, these FETs are low RDS, so they won't be generating humongous amounts of heat anyway. So the SILPAD 900 is absolutely fine, and I've been doing that for the duration that I've been repairing these amplifiers, and that has not caused any issues. So yeah, that's about all I've got to say about these for now. If you've got any questions on these, make sure to leave me a comment in the comment section. And if you want to be able to catch me do some amplifier repair live streams, make sure that you do subscribe and tick the bell icon so that you know when I'm going live. It should tell you most of the time. And if there's any amplifier styles that you'd like me to cover, or anything, like I say, anything that you've got questions on, I'll try and answer you best I can, based on my current experience and knowledge and whatever. So yeah, until next time guys, have a great one, take it easy.